Good morning, I'm Vincenzo Marco De Luca from Università of Trento, and today I'm going to present our recent work xAI-Drop. xAI-Drop merges three different topics: graph neural networks, explainability, and regularization. Our idea starts from the fact that often in graph neural networks for regularization they are used random dropping strategies. Our idea is to design a method that attempts to localize nodes which are responsible for overfitting. This leads us to define the so-called noisy nodes. And the definition of noisy nodes comes from the plot that we can see here. We collect statistics on a graph neural network dataset and architecture that shown how often in a graph neural network, when the model enters into the overfitting regime, we have that the explanation quality start decreasing. So there is an information coming from the training data that tells us something about the validation ones. And these lead us to define an OSI node as a node for which the model has high confidence in prediction but low normalized fidelity sufficiency. So the model feels sure about the prediction it is doing, but it is not able to explain it well. Then, to apply this approach, of course, we need an explainer. More specifically, we use the gradient-based explainer because they are really effective. And as an explanation metric, more specifically, we use the normalized sufficiency. Sufficiency tells us if the explanation is sufficient for having as output something similar to what we had as output by feeding as input the entire input data. And it is a score, so if fidelity sufficiency is equal to 1, it means that the explanation is really good. Otherwise, if the explanation is not good, it will tend to 0. Then the xAI-dropping procedure is applied as follows. So at each training time, do we have to compute on training data in case of inductive setting or on the entire set of data in case of a transductive setting, the confidence of the nodes. Once we get the confidence, we have a threshold, we have to fix a threshold theta in order to get a binary mask on the input samples. These binary masks tells us which are the confident and non-confident nodes. The confident nodes are the ones that I colored in orange, and we need to compute the fidelity sufficiency on top of them in order to get a score of the quality of the explanation for these nodes. Once we get this score, we need to map them into a Gaussian distribution by means of the Yeo-Johnson transformation. Of course, we need to reduce the probability of dropping for node having high fidelity sufficiency. Since we want to retain the nodes having good explanation, but we want to remove the nodes having a bad explanation. And then we need to apply a Bernoulli distribution to decide which are the nodes to retain, which are the ones to drop. Then, of course, when we drop a node, we will drop also the edges in his neighborhood. Here we have the results. First of all, we can analyze the node classification results that we tested on three different datasets on three different architectures. We outperform both random strategies, but also learning strategies that learns by means of a parametric procedure the best topology for a given network. And we outperform also xAI-based strategies that are based on different kind of procedures, such as MATE that is based on meta-learning, XPath that is a modular procedure, or Engage that is based on adversarial attack. But since our framework is quite general, we can extend it also to link prediction, since we just need to have a confidence value, we need an explainer, and we need a metric for the explanation. Then, of course, when we apply link prediction, we will drop the edges, since they are the samples on which we have the confidence score. That's it. Thank you for the attention. For any kind of question or curiosity, you can send me an email. Have a nice day. Bye bye.